So it's a pleasure to visit the department here. Thanks for inviting me. It's actually my first time in KAIST and also in Korea. So I must say I really enjoy the kimchi and all this stuff. And this talk today is going to be about some coloring problems that came up, like this new coloring problem came up when I was in the last year of my PhD. I'm trying to make everything really simple and elementary, so please feel free to ask any question. I prefer a more interactive talk than a speech, because then I might fall asleep. So you have to wake me up. Okay, so the title is Conflict-Free Coloring, and let's just go straight to the point. So this is defined for arbitrary hypergraphs. So what is a hypergraph? A hypergraph is a pair of sets, V and E, where in our case V will always be assumed to be from finite set, and E is a collection of subsets of V. So it's a subset of the power set of V. And this notion is not my notion, it's a classical notion of a proper coloring of a hypergraph. A proper coloring is just a function from the vertices to some numbers, say, or any finite set, which we call the colors. So here we denote them by 1 to k. It's a k coloring. And we say that this coloring is proper if no hyperedge is monochromatic.
Hyperedge is one of these subsets.
One of these subsets in E. So every element in E, which is a subset of E, should not be monochromatic. I actually should be more accurate and say every element in E which contains at least two vertices of E. Otherwise, we cannot do anything. So it's a proper coloring if every such hyperedge that has at least two vertices is such that not all the vertices have the same color. So there are at least two colors there present. So this is a classical generalization of graph coloring, where a graph is simply a hypergraph where all the elements in E are just pairs, just have cardinality 2. And the chromatic number of a hypergraph would be just the minimum number of colors needed for any proper coloring. So the coloring that uses the minimum number of colors, that number is the chromatic number of the hypergraph. And this notion coincides with the classical graph coloring when the hypergraph is just a graph. So if we have a graph which is a finite set plus some collection of pairs, a non-monochromatic coloring of such a pair must mean that the two endpoints, the two of the edge, have different colors. So it's just a graph. I want to talk about a more restricted generalization of a hypergraph, which we call conflict-free colorings, or CF coloring in short. That would be requiring, so it's a coloring, again it's a function that assigns some elements which we call colors to the vertices in such a way that now every hyperedge has at least one uniquely colored vertex. Meaning that every hyperedge, there exists a vertex whose color is different from the colors of all the other vertices in that hyperedge. And the chromatic number, the CF chromatic number, high CF of H, is the minimum colors needed for such a coloring. Let me give you an example. So the first non-trivial example should be actually what is called a 4-uniform hypergraph, because for a graph, if we have just some graph, so this is the set of vertices, and those are the pairs. This is a subset of size 2, a subset of size 2, and so on. If you color it in such a way that every edge has one uniquely colored vertex, so one color that is distinct from all the other colors, and there's only one more vertex, it means that those two vertices must have distinct colors. So it's just the graph coloring. Actually, if you think about also for 3-uniform hypergraphs, so those are hypergraphs for which all the subsets in E have cardinality exactly 3. That's a 3-uniform hypergraph. So if you have 3 vertices and you color the vertices, if you have a triple and it's not monochromatic, so there are at least 2 colors there, it also means there is one unique color there. It cannot be that all colors appear at least twice for 3. Just check the cases. So the first non-trivial case where these two notions are separated is for a full uniform hypergraph. For example, let's consider the hypergraph where we take two sets, say, of n vertices, so n over 2 vertices here, or let's just call it n. So we have n vertices here, n vertices here, and the hyperedges are all quadruples that are consist from some pair here and some pair here. So you take any possible pair here plus any possible pair here. These four guys, that's a hyperedge in the hypergraph. So we have, how many hyperedges do we have? We have n choose 2 times n choose 2. So now, how many colors do we need for a proper coloring of that hypergraph? Just 2. I mean, just color all these vertices with color 1 and all these vertices with color 2, and no hyperedge is monochromatic.
So this is the proper color.
This is a proper coloring. So if this is H, then chi of H is exactly 2. It's not 1, so therefore it's 2. It cannot be 1. What is the CF chromatic number of H? Well, you can see that you can color it with n colors. For example, if you color all these n guys with distinct colors, 1, 2, 3 to n, and then just give all the colors here 1, all the 1, you can check that any hyperedge has a unique color. You cannot do less than n. Why? So I claim that this is n. So why can't you do less than n? Suppose, well, if all the vertices, if you color them, a CF color, if all the vertices are colored distinctively, then you use n colors. So the other case is there are some two vertices that you decided to give them the same color. Let's call it color I and I. So you color both of them with I. But this means now that every pair of vertices must have different colors here. Because if there would be two vertices that have the same color, then this hyperedge consisting of these two vertices plus these two I have non-uniquely colored vertices. Every color appears there twice. The I appears twice, and right? So this means that this side have n distinct colors. So in any case, if you CF color this hypergraph, you use at least n colors, and n colors are enough, so the chromatic number of this hypergraph is exactly n. So it's already separated from the non-monochromatic. Okay, now the question that first arises, why the heck do we come up with such a coloring? Why is it interesting? So let me convince you that it is interesting, at least for some communities. So I'm going to focus mostly in this talk about geometric hypergraphs. What are geometric hypergraphs? So geometric hypergraphs are those that can be realized by nice geometric objects, as, let's say, the Venn diagram of those objects. For example, here I have a hypergraph that consists of 4 vertices that are represented by those ellipses. And the hyperedges are all subsets that could be defined by taking a point and considering all ellipses that contain this point in the interior. So for example, here we would have these 4 ellipses are the vertices, and the subsets that we have are all these subsets. The reason I wrote, for example, 2 and 4, because only if I can find a point that is contained in exactly the ellipses 2 and 4. I cannot take a proper subset. I take everything. So, okay, you have the singletons, 1, because this is a point contained only in 1, this is a point contained only in 2, and so on. You can check that. Of course, I might have been wrong, but yes? Questions? Okay. So this is, I would call the hypergraph defined by those ellipses, or induced by those ellipses. It's simply the Venn diagram of those objects. What is the motivation? Well, consider the following question or problem. Suppose we maintain some cellular network, and we have a bunch of antennas, and those disks represents the area of coverage of the antennas, say. They might have different radius because of different power. Now we have clients with mobile phones somewhere. They can be anywhere. So this guy. And this guy, in order to connect to the network, it needs to choose one of those antennas that cover his location and talk with that antenna and then connect to the network. But those antennas are pre-assigned fixed frequencies. So for example, it might be that this antenna uses only frequency, let's call it frequency number 1. So this guy can just tune his phone and transmit in frequency number 1, connect to the network. But the problem arises when there is another antenna covering that client that also uses frequency number 1. Then we have this mutual interference that occurs, and we have a problem. But we can resolve the problem as long as there is at least one antenna covering the client whose frequency is distinct from all the other frequencies, say 2. So for example, if we give this antenna frequency number 2, then this client can talk to this antenna and he has no interference from other. And we want this property to hold in any possible location. So what we want is that in any given point, we have at least one unique frequency among the frequencies assigned to those antennas that cover that point. So if you think about it, we want to conflict-free color this hypergraph that is induced by the set of disks that are defined by the antenna. We want that so the elements are the antennas or the disk, and for every point we look at the set of all antennas, the subset of all antennas containing that point. We want some uniquely assigned frequency, and that's the coloring. The frequency assignment is coloring. And of course, we would like to minimize the total number of frequencies we use because the frequency spectrum is really limited and costly. Actually, it's not, I'm not just saying, I actually heard from the industry that it's becoming a serious problem, the availability of spectrum. This is one motivation to study CF coloring. Another motivation, let me give you sort of a twist on that model. We can also think of another hypergraph where we have points in the plane. So the points might represent the location on the antenna, but the coverage now is defined by the power of the client. So a client might have a very powerful cell phone which can reach this set of antennas, say, a disk, and we want that among this subset of antennas as one unique frequency. And we want this to hold to any possible disk, for example. So in this case, we will get a program where we have some finite set of points in the plane, and we want to color those points in such a way that every disk, no matter how small or big it is, if it intersects the antennas, then at least one of those antennas have a unique frequency, a unique color.
So this is different from the other?
This is slightly different than the other. We will see in a few minutes when we start analyzing this. Another motivation is what is called RFID networks. So RFID stands for Radio Frequency Identification Tag. So this could be passive devices. You probably have it if you have on the toll highways here. Maybe, I don't know, maybe the bus I saw is not really paying the toll booth here. So this could be something without a battery, just a chip that is passive and stores some information. But the thing is that in order to read this information, you need a different device, which is the reader. That's the one that's usually somewhere near the toll booth. And this reader can read the information there by sending electromagnetic wave. And the way this device, the RFID tag, somehow by induction, it returns the energy in such a way that the reader can get the information stored there. And actually, it is being used in Legoland, in Denmark. So people come with their children to Legoland. It's a big place. The child gets a little RFID tag on the wrist, and they let them wander around, and then they go to a screen, they can see where the child is. How is that done? So here is the problem. Suppose those are the children, those are the points in the plane, they all have some information stored. And what you want to do is you want to read this information as fast as possible. But in order to read this information, we have these readers scattered around. Those are the readers, say they are disks, like that. Okay? So the readers, so one reader can initiate a read action and get the information from all the tags in its coverage. The thing is that they all use the same frequency. So if a tag is being read at some time by two readers, they initiate the same reading action at the same time, then they might interfere with one another. And we want to sort of schedule, so we cannot just let all the readers in one time do a read action and get the information. We need to do it cleverly. We need to, so let's assume that a tag can be read at a given time only if one reader is trying to initiate a read action at that point. So now we want to schedule the readers to read the information. By scheduling, each reader must be assigned some time slot, and it means that it does not do anything until that time slot. And at that time slot, it initiates the read action. And we want the property that for any point will be read eventually. So we want the property that for any point there is some time slot such that only one reader, exactly one reader, is trying to initiate at that time slot a reading action, and this reader covers that point. If you think about it, if you think of the time slot as the color, what we want is that for any point, we want to assign colors to those disks such that in any point, and the colors represent time slot, so at any point there is some unique color there, meaning some unique time slot. Some guy that have a unique time slot, so only this guy will try to read that information in that time slot. And we want to do it as fast as possible, so we want to minimize the total number of time slots we use. So this is exactly a conflict-free coloring of those readers. Actually, with respect only to the hypergraph defined by the hyperedges for which we put a point. So is that clear, the motivation? Okay. Actually, we found quite a few. We color the disk now. We find quite it's actually surprising that by now we have very many more motivations and also some deep connection to other mathematical areas has to do with discrepancy and geometry. I'm going to skip now the PR part and go to the business. So I said that already. So let's analyze a very simple case. So the case is where we take an example of a family of hypergraphs that are defined as follows. I fix a finite set of points in the plane. I want to color these points with a minimum number of colors in such a way that every disk contains at least one unique color. So I want to color the points here. I'm coloring the points. See, the numbers are the colors. So here is the coloring, and I want the property that any disk contains some unique color. So you can say, hey, we can take a disk containing all the points. There must be a unique color, so it must be globally unique. Nobody has this point. Oh, that's true. So you always have one color which is globally unique. But you need more than that. You need the fact that any disk, no matter, for example, this disk that contains these 2 points colored with 3 and 1 point colored with 1, then we have this one which is unique there. And we want it to hold for any possible disk. And the natural question that arises is how many colors do we need in the worst case as a function of the number of points? So let me show you, yes?
So now you're looking over all possible
disks, all possible subsets of points that could be cut off by a disk. So the hypergraph is a set of points plus all possible subsets that could be cut off by a disk from the rest. How many colors do we need in a worst case? Let me show you that you might need at least as log n, so it's not a constant. And it's very simple observation. Just place all the points on a line, some line. And now, coloring the points with respect to disk is equivalent to coloring the points with respect to intervals, because the disk intersects the line in an interval. So so if you color the points in particular, it means that every interval you choose, there will be a unique color in that interval. So in particular, if you color the points correctly, I will take an interval containing all the points, and then there's some unique color. Let's call this color 1. I don't know where the point is colored 1, maybe this point. But I can always go to the right or to the left and find an interval not containing that point, but contains at least n minus 1 over 2 of the points, roughly n over 2. So I take this smaller interval. Maybe my drawing is not so accurate. This should not contain this point. So now in this interval there's some unique color, but this unique color cannot be 1 because 1 is only that point has color 1. So let's call this color, the new color we found, 2. It's somewhere here. I don't know where. Now I can take a smaller interval containing at least roughly quarter of the points, which is contained in the previous interval, and does not contain point color with 1 nor point color with 2, but it still has to have a unique color. So let's call this color 3, and I can continue like that roughly log n times, right? So I can always find log n colors no matter what the coloring was if it obeys the CF property. But you might say that I'm cheating now. This is really a degenerate case. It's completely, that's not the general case. It's very, the general case would be probably that every 3 points are affinely independent. This is completely not the case, and maybe it's irrelevant. But actually, not really true. So you can do it for, you can just place any endpoints in general position, let's say on a convex curve. And now the hypergraph defined by taking disks contains this intervallic hypergraph. So any subset of consecutive points on that curve, for example, this subset that lies below that line, every subset of consecutive points by definition could be separated by a line from the rest of the point. And so they are contained in some half plane. What is a half plane? Infinite combinatorics. It's a big disk, right? So take any subset of consecutive points that you can separate from the rest by a line, then there is also a disk that witness this subset. So all these interval subsets, they exist there, so the same analysis as before would prove that no matter how you color these guys, you needed at least log n colors. Actually, sort of an intermediate question arises, can you come up with a nice set of points that will require a constant or less than log n colors? And surprisingly, the answer is no. So actually, the lower bound is even stronger, as was proved by Pach and Top. So they proved that, somewhat technical proof, that any set of endpoints, no matter how not general they are, would need at least omega of log n. Omega means there's an absolute constant there, and it's always at least that constant times log n colors. So the lower...
It's at least this many.
At least this many points. Any set of endpoints, not only that there exists a set of endpoints, any set of endpoints need at least that many colors. Okay, what about sufficiency? What about upper bounds? So if we go back to this very degenerate case of points on a line, you can probably see that I use the word divide and conquer because I gave the talk also in some computer science departments, but here I should use the word induction. So log n colors also suffice simply by coloring the median point with 1 and use induction on the right and hand side, reusing colors and keeping the set of colors distinct from 1. So something like that. So I can use 1 and then I use 2 like that, 3, 2, 3, and then I copy the same coloring to the left side. So you can see that in this way I use only log n colors. The reason that this coloring is good is very simple. If your interval contains only points to the right of the median, then by induction it is served, there will be some unique color. If it contains only from the left, it is okay. And if it contains both the points from the right and from the left, then it must also contain this median point. And nobody has color 1, so it's also... So it's an easy exercise actually to program. But what about our problem? Coloring points not necessarily on the line. Oh, this would not work, this sort of partition argument, because if I take a set of points, can you see here? If you take a set of points and you say, for example, if you choose some, if you project them on the line, choose the median point and color it with 1 and try to recurse on the right and left side, it is not true anymore that if you have a disk containing points to the left of 1 and points to the right, then it will also contain this point, right? I mean, this disk, for example, can contain points both from the left and right, but not 1. So you need to do a different trick, and here is the trick. So let me show you this first theorem. So we can define this function f of n, which is the minimum number of colors needed for a CF coloring of points in the plane with respect to disks for any set p of n points. And the theorem says that order of log n colors always suffice. So it's at most, actually it is not the accurate constant, it's like log to the base of 4/3 of n. That's what we have. So let me show you the proof. So it's a constructive proof. So it gives a very efficient algorithm to color a given point. And here is the construction. Let's consider the following graph defined on the set of points, which is called the Delaunay graph. Delaunay graph are just all pairs of points that could be cut off by a disk. Basically, it's the edges of cardinality 2 in our hypergraph. So we take this graph. For example, these 2 points, there is a disk containing only them. Therefore, it's an edge in my graph. And I will even draw this in the plane by drawing the straight line segments connecting these 2 points. And then I needed to do it for any possible pair of points. And apparently, what I get is a planar graph. This is a well-known, it's actually an easy exercise to prove that such a graph, this drawing of the graph is a plane drawing. And now what I need is, well, I'm using the 4-color theorem, even though I don't really need it, but the 4-color theorem says that every planar graph could be, the vertices could be partitioned into 4 classes such that each class is independent, meaning that no pair of points in that class are connected by an edge. So, in particular, it means by the pigeonhole principle that one of the color classes is big. It has at least 1/4 of the points. So, there's always a large independent set in that graph. And I'm going to take this independent set. Where is it? So, there's always a subset S such that S has at least n over 4 vertices and S is independent, meaning that no 2 points in S are connected by an edge. So meaning that no 2 points in S could be separated from the rest by a disk. That's what it means. Keep in mind. So I'm going to, I need to completely color the points, so I'm going to completely color, I'm going to start with coloring the elements in S by color, let's call it color number 1. All the elements in S get color number 1. And then what I'm going to do, I'm going to remove S. And so here we find a subset of the vertices, no 2 which are connected by an edge. And I'm going to give them the final color 1. And now I'm going to remove them from the set, discard this subset. So here I'm discarding the subset and iterate on the remaining set of points doing exactly the same thing. So now construct again the Delaunay graph on the remaining set of points. So here we have this graph. Okay, so you only consider what is remain, and then again you look at all pairs that can be cut off from the rest by a disk and so on. Take an independent set. Here is an independent set. Color them with the next color 2 and remove them. And now we are left with basically a triangle. You see each pair could be separated from the rest by, so this is a clique. The largest independent set is of size 1, so we just give them 3 more colors, 3, 4, and 5. And now, how many colors did I use? The number of colors I used equals the number of iterations I did. So in each iteration, I discarded at least 1/4 of the remaining points. So if I take a set and each time I throw away 1/4, how many times until I discard all elements? That's easy to see that it's roughly log n. Right? If you throw away 1/4 of your elements, it will not go to infinity. You will end up after roughly log n iterations. So the number of colors is log n. But the question is, why is it a valid CF coloring? And that's what we need to prove. So we need to prove that, here is the coloring, that no matter what disk I take, there is some unique color in that disk. In fact, we're going to prove a stronger property, that the maximal index color is the unique one, for sure. Maybe there are more unique colors, but if you take the maximal index color in that disk, it must be unique. And to prove that, assume to the contrary that this maximal color in a disk is not unique. So let's call the maximal color I. And suppose I is not unique. Okay? So let's ignore colors in that set of points inside the disk that were colored with a color less than I because they were discarded before the ith iteration. Let's look at the ith iteration. Let's jump to the ith iteration and see what happened there. So this is the ith iteration. This is the set of points remaining there. And now we have constructed the learning graph, and you took an independent set and colored this independent set, all of the elements with color I, and in particular these two guys were colored with I. Okay? But why have they been colored with I? Because they belonged again to the independent set. What does it mean? It means that there was no edge between them. Why wasn't there an edge between these 2 points? Because an edge is placed between 2 points if I can find a disk that separates these 2 points from the rest. So there was no edge because no disk would have separated these 2 points from the rest. In particular, this specific disk that we want to prove something about it did not separate these 2 points from the rest of the point, meaning that there must exist a third point. Okay? So these 2 points are independent. This is a disk that does not witness a Delaunay edge, so there must exist a third point. What is the color of that point? It cannot be less than I because we already ignored these points. We are now in ith iteration. It cannot be more than I because I is the maximal color that we could find in that disk. It's not a contradiction yet. So it only means that if it must be I, the color. So now we have a disk containing some bunch of points colored with I, and we want to find a contradiction. But we use a simple geometric lemma, but it needs a technical proof that if you have a disk containing some set of points, and some points inside, some point, or even on the boundary, and some points are outside, then you can find another disk like this that contain exactly 2 points from the interior of that disk, but no point from outside. It does not mean that the disk is contained in the original disk. It just means that there is some disk that captures only 2 of the points, but none of the points outside. But this means that these 2 points must have formed an edge of the Delaunay graph in that iteration, but a contradiction because those 2 guys are independent. So this is a contradiction. So this is the proof. So we need this. So what we use here, even though I talked about points in the plane and disk, and it's in very restricted family of hypergraphs, what you saw here is rather more general. Except for this technical lemma that basically what I needed is that this hypergraph has the property that in any sub-hypergraph, which is the one taken by taking a subset of the disk and looking at the induced hypergraph, which is, never mind for a second, but we need the fact that every hyperedge also contains some hyperedge of cardinality too. That's what we needed. And that's not true in general, even for nice geometric hypergraphs. So again, there's some framework suggested here that's saying the following. Given any hypergraph, okay, this notion of the Delaunay graph is very general. So we want to find a large independent set, V prime of the Delaunay graph, which would just mean all pairs of all hyperedges of cardinality 2. This is a graph that comes from the hypergraph, and you want to take a large independent set in that hypergraph. take a large independent. Why large? Because if we're going to discard each iteration a large chunk of the elements, so we'll discard all the elements in a small number of iterations, which is the number of colors. And then we will color all these elements with the same color I, and then recurse on the remaining set of vertices. So we need some hereditary property that maybe in each, and then consider the hypergraph induced on this set of vertices. So you take the hypergraph for which this is the set of vertices, V minus V prime, and the hyperedges are all the original hyperedges intersected with this set. It's the induced subhypergraph. But we need one more property, which is this shrinkability property, that every hyperedge in every such hypergraph contains an edge. And this is not true. Yes?
Does that mean a two-element?
Yeah, every subset contains also every subset in E contains a subset of that subset of cardinality too. But this is not true in general. But it is true, for example, for this hypergraph. So what is this hypergraph? Now just replace the word disks with axis parallel rectangles. The question becomes much harder. But all the ingredients are there. I mean, you can talk about this Delaunay graph. You take all pairs for which there is some axis parallel rectangle containing a pair of points, like here, this edge, and so on, and try to find a large independent set in that graph. So it's a very simple question, or even try to bound the chromatic number of that graph. So very simple question. Here is an open problem. You have a set of points in the plane. You connect two points by an edge. If they can be separated by an axis parallel rectangle, give some bounds good bounds on the chromatic number of that graph as a function of the number of points. Widely open. The only lower and upper bound are exponentially apart. Yes?
So this is maybe just a combinatorial question, right?
This is a combinatorial question. It's basically a question about the Haas diagram of partial ordered sets, or in less fancy words, you fix a permutation. I mean, any two points which would have the same, if you sort them from left to right, and you look at the permutation induced on the y coordinate, so if this is 1, 2, 3, 4, 5, 6, 7, then the permutation is, right, 7, 6, right? This is the 6th point here, and so on. You look at the permutation. Any two set of points that gives you the same permutation has the same answer. It's a question about permutation. Widely open. It seems rather hard. So recently, Ajwani et al. Improved the, with this pellet, we noticed actually we have a few elementary, very simple proofs that root n colors suffice to color this graph. One can use the Erdo-Sekeren theorem for real. It's an exercise, or some other tricks. Then it was improved by Noga alone to root n over root log n. And recently it was improved to n to the power 381, and this tilde above the denotes some log factors, polylog factors in the big O notation. But only recently, Chen, Park, Segedi, and Tarbosh could show that actually this graph does not have a constant chromatic number. We thought that maybe there is always an absolute constant, such that this graph is always have chromatic number at most this constant, and they proved that it can grow to infinity. Actually, we will show it the rate of something like log n, at least log n over log n square. Okay, so this is a nice question that came out of this business. But what about for this graph? So again, I mean, if you have some bound on, like for example, if you have a bound on the Delaunay graph, basically it immediately translates to the same bound for the conflict-free chromatic number, but with a higher constant in the big O. Because what it means is that, whatever, if you have n to the alpha upper bound, then there is an independent set of size n to the 1 minus alpha. So you discard n to the 1 minus alpha at each iteration, and then you can check do the math and see that the number of iterations will be some constant times n to the alpha. If it would be log n, then it will translate to a log square n and so on. But this is all shrinkable hypergraph, so any hyperedge has an edge. But here is a, so this framework does not work for disks, for example. So now we go back to the original question about coloring disks, not points. There we, suppose we want to color these 6 disks, okay? So the hypergraph again is the Venn diagram now. The disks are the elements, and those, for example, this point here means that the 3 little disks, the only one that contains this point, is a hyperedge in that hypergraph, subset of phi 3. But this is not a shrinkable hypergraph. Here, this point, okay, these 3 disks form a hyperedge, but no 2 of them form a hyperedge, right? There is no point that belongs to exactly 2 out of the 3 disks. And not only that it's not shrinkable, if you try to use the framework, then in the Delaunay graph, by definition, these 3 guys are independent. There is no edge between 2 of them because there is no point that stars only 2 of them. There is no hyperedge of size 2. So they are independent. So I might take them and color all of them with 1, but already then I'm wrong. If I color these 3 guys with the same color, this is a hyperedge for which all elements are colored with the same color. So the idea is simply not to take the Delaunay graph. Take the whole hypergraph, and instead of coloring the graph, we color the hypergraph in a non-monochromatic way, which is a stronger coloring. So here is the sort of adapted framework. So now, what I want to do, and what I'm going to present now is a very general framework that does not need shrinkability. It works for any hypergraph. I chose this just to demonstrate it, but we don't need that. So any hypergraph could be colored. So as long as we know something about proper coloring that hypergraph with small number of colorings, this translates to a sea of coloring of that hypergraph with a small number of colors. And here is the idea. Instead of coloring the Delaunay graph, color the Venn diagram, color this hypergraph in a proper way, meaning that no point is covered by a monochromatic set. Okay? So suppose I know how to do that with a small number of colors. For here I use 3 colors, and you can check that every point that is covered by at least 2 disks is not monochromatic. Well, okay, this color is that color. So take the largest color class, that would be the analog of an independent set, and color all the disks in that color class with the same color 1 and remove them and iterate. Color the remaining objects or the remaining hypergraph in a non-monochromatic way and take the largest color class and give it color 2 and iterate and so on. So this would be 3 and 4, and that's our coloring. Okay, that's a very simple no. And now I'll prove to you that this coloring is indeed a conflict-free coloring. And here is the proof. So and this framework is good for any hypergraph. So basically, I'm talking about hypergraphs, about Venn diagrams, but you can think of any hypergraph. So basically, if you have a bunch of shapes in the plane that you want to color, as long as, so here is the algorithm, construction. So as long as the set of shape is not empty, you find the proper coloring of whatever remains from the shape of the hypergraph in this very shape. You take the largest color class and color it with color I, and then increase I by 1 and recurse on the remaining set. So basically, I take a hypergraph, I have vertices and hyperedges, I color the vertices in the proper coloring, I take the largest color class. The proper coloring is an auxiliary coloring. I take the largest color class. Those vertices in that class would be colored finally by 1. Remove those vertices and do the same on V minus this set, on the remaining set of vertices. So you need the proper coloring of the new induced subhypergraph and so on. Why is this framework correct? So again, the maximal color of any shape, So given a point, look at all the shapes covering the point. So look at the hyperedge and look at the maximal color in that hyperedge. That's going to be unique. And the reason is, I mean, this is a general proof for any hypergraph, but let's just think of it like that. So take a point and look at the shape among shapes covering that point that has the maximal color, and assume to the contrary that it is not unique. So there must have been a third shape, but basically the reason that I colored in iteration I both shapes with color I, because they belong to the same auxiliary color class. So suppose this color is pink. Okay, so there must have been, so this auxiliary coloring had the property that it is not a monochromatic coloring, so there must have been another color in the auxiliary coloring covering that point, but this color is not pink. But in that iteration, I only discarded pink guys. So what is the color of this non-pink eye? It cannot be I, because in I, those that are colored with I are only the pink guys. So now this green guy is not colored in that iteration, so it means that it was colored somewhere in the future, contradicting the fact that I was the futurist colored shape. And that's a contradiction. And the question is, the key question that now arises, how many colors can we use for the auxiliary coloring? Because if we use a small number of colors for the auxiliary coloring, the largest color class by the pigeonhole principle will be big, and then in every iteration you will discard a big chunk of the vertices and will end up with a small number of iterations. So basically we need to bound the chromatic number of the underlying hypergraph. And if we speak about geometric hypergraphs, for example, we spoke about this, and I never told you what's the result. How much time do I have?
7 moments.
Oh, okay. So let me show you that if you take the Venn diagram of this, then the chromatic number of this hypergraph is 4. In fact, it's a very simple equivalence of the 4-color theorem. So the 4-color theorem statement is equivalent to saying that you can color a bunch of these because 4 colors so that no point is monochromatic. That's equivalent. So one direction follows from, I'm going to show you in a minute. Let me just say that if I have x is parallel rectangles, then I can show that the chromatic number of the Venn diagram of x is parallel rectangle is at most 8 log the number of rectangles, and this is almost tight. I mean, this is sharp bound because Pat and Tarbosh provided a matching lower bound. So they're constructing this elegant construction of a bunch of rectangles that require in any proper coloring at least log the number of rectangles colored. So a more general result is that says that this chromatic number, the proper coloring, the chromatic number of some shapes in the plane has to do with what is called the union complexity of the shapes. So what is the union complexity? So if the union complexity is small, then also the chromatic number is small. Let me show you in short what is the union complexity. So in particular, it means that if you take a bunch of simple closed Jordan curves and look at by the Jordan curve theorem, you have a shape, which is only one shape, so if you take any curve, which is a simple closed Jordan curve, so there's always, by the Jordan curve theorem, there's also an inside and an outside, so we're going to consider the inside. This is going to be our shape. And if those curves have the property that they behave like circles combinatorially, in the sense that if I have a bunch of these guys, and every two intersect in at most 2 points, so a bunch of fully dimensional bodies like that every two boundaries intersect in at most 2 points, I call this family a family of pseudodisks. So pseudodisks, I can prove that if you have a bunch of pseudodisks, then the chromatic number of the underlying hypergraph is bounded by some constant. I don't know exactly if the calculation constant is not 4, it might be even 4, which is tight. So what's the relation between chromatic number and union complexity. What is union complexity? If you take a bunch of Jordan regions in the plane, the definition of union complexity is just simply the number of vertices which are the intersection of pairs of boundaries that lie on the boundary of the union of the shape. So if you look at the union of those four shapes, you look at all intersection points of boundaries that lie on the boundary of the union. So this is a point on the boundary of the union, this one, and this one, and this one, right? So the complexity here is 1, 2, 3, 6. Okay? And suppose we have a family of regions such as pseudodisk or something that have the property that there is some function on the integers for which the union complexity of any n regions out of this family has union complexity at most u of n. Then the chromatic number of the underlying hypergraph is at most order of un of n over n. For example, it is a well-known result about pseudodisks, and as remind you that pseudodisks, here is it's a property of a family. It's not a property of a shape. So these guys behave like pseudodisks because every pair of them has the property that there is intersecting at most 2 points. So, oops, another one. Pops up. Oops, another one. So here's a nice result of Kedem et al. That says that the union complexity of any n pseudodisk, so they don't even have to be convex or anything, is at most 6n minus 12. So by the result I just stated, so u of n here is 6n minus 12. So u of n over n is a constant. Actually less. So by the result I stated before, the chromatic number of this hypergraph is constant. I will not have time to show how to prove this. But then this means that if you want to confix recolor those shapes, at any iteration we will use what? We can use a proper coloring that uses a constant number of colors, then a fraction by the pigeonhole principle, some constant fraction of the elements will belong to the largest color class, so I will discard a constant fraction of the elements and I'll end up with a log n, order of log n number of iterations. That would be a conflict. 1 minute. Okay, so maybe I'll skip this. Maybe you're tired. So you see, one problem is that, for example, if we talk about coloring axis parallel rectangles now, themselves, not point, then the union complexity could be quadratic. Here, n over 2, and n over 2 like that, and you have quadratic number of vertices that lie on the boundary of the union. Therefore, u of n, I cannot say that it's better than n square, and n square over n is n, and saying that you can proper color n such shapes with n colors is trivial. So it means nothing. But one can do better by doing some divide and conquer construction and noticing that if all of them are intersected by a line, then the union complexity is linear, and then you can color those guys in the middle with a constant number of colors and recurse on the right and left. This will give you a log n. I'm going to forget about it. Just believe me that one can do it. Disks, I won't even. So let me summarize maybe. So you claim I have 1 minute. Minus 2. Maybe I should. Too much. Maybe I'll just stop here. Okay. Yep.